every instrument produce sound based on the concept of stationary waves. Okay, any instruments, guitar, bass, or flute, saxophone, okay, any types of instruments that uses strings or sound, it works based on stationary waves. So what is really stationary? Let's take one example. Let's take a guitar. Okay, when you pluck a guitar string, okay, when you pluck a guitar string, you hear a tone, right? You hear a certain tone, and the tone come to us as a combination of frequencies. The tone come to us at a set of frequency. It's never just one frequency. Okay, the tone that you hear is like a bunch of frequency together come to you. So here, if I draw the string, let's say we pick a string with a certain length, right? So we have two fixed points, and then we have a string here. Now two fixed point because the both this pointer, it cannot move, right? There's no motion here and here. So we would call this note. A point of no motion, we call it as note. Same here, we have two notes. This is another note. No motion means that the string, the particle cannot vibrate at that 2 points. Now, as I pluck the string, I will create a wave that travels along the string. Here, from left to right, it will travel here. Now, what happens when the wave hit the note? When the wave hit the note, it will be reflected back, right? And as it reflects back, it will superimpose with the original wave that you created. Again, when you create a wave, the wave has a certain speed, okay? It has a certain speed, it has a certain frequency, and it moves along the string. As it hit the note and then bounce back, reflection, there will be reflection at both the notes. And reflected back, this reflected wave will interfere with the wave that you created, with itself. The wave will interfere with itself and then create a resultant wave. Okay, so based on the principle of superposition, what the superposition says, when you have a crest joined with another crest, becomes what? Double the amplitude, right? If you have a crest joined with a trough, it becomes zero amplitude. Okay, so when you pluck the string, what you see, the pattern of the vibration that you see on the string is a result of the combination of the two waves. This one, very important, you need to understand. The pattern that you see when you pluck the string is a resultant effect of the two waves joining together. Which two? First one is the one that you create. Second one is the reflection of the original wave. Okay, so because the wave is reflected, right, and it comes from the same wave, from that original wave, so it has the same speed. It has the same speed, it has the same frequency. So standing waves or stationary waves is created when two waves having the same speed and same frequency combine. And the only way to achieve this is by reflection. Because if you pass two waves, you have to make sure that they have the same speed and they have to make sure that they are coherent, they have the same frequency. The easiest way to make sure that this is fulfilled is by reflection. Okay? Right. So if you look at any point on the string, pick any point on the string, it is the result of the two waves. It is never just one. So what pattern you will see when you vibrate the string? Okay, here's one pattern here. There are many patterns that you will see later. We'll go through each of them. But one of the pattern is like this. Okay, so the dotted line shows that the movement of the string. Okay, so again, we have two notes. here. And then you'll see, you'll realize that there are few points on the string that there will be always zero amplitude. Okay, there are some points on the string remain zero amplitude, not moving, like the middle one over here. Here, again, a point of no motion, what do we call it? Another note, right? So you have another note here. So here, this pattern, you have 3 notes. What is happening at the note there? The note here is where the destructive interference take place. Okay, so destructive is like you have a crest combined with a trough, so you get 0. Okay, it happens that all the time when the wave bounce back and forth, all the time that the center is always 0. It's always a destructive interference. So you have created a note over here that does not change. Over time, you'll see that this one remain as a note. Right, so what happened to the string here? The string, it bounces back and forth like this. Here, if between in between 2 notes is what we call the antinote, right? Antinote. So antinote is the point where it gains amplitude, right? So we have antinote here, and then we have antinote here, and then the rest is note. Yeah. Now, antinote is the resultant amplitude, right? So you have the amplitude over here is the amplitude of the 2 waves add up. So it's bigger than the original wave, the amplitude of the original wave. Okay, it's double the amplitude. So what is happening to the antinote here? The antinote is bouncing back and forth. It's like the string is dancing up and down like this. Okay, as you vibrate, you see the string is dancing up and down, and it appears as if it's not moving at all. That is why we call it stationary. Okay, stationary, not moving waves. So it looks like it is not moving. The wave is not moving. It's like just dancing around like this. But understand that what you're seeing is the stationary wave, right? But how is this created? This stationary wave is created by the combination of the 2 moving waves. The 2 moving waves. One is the original wave, the other one is the reflected wave. So you need 2 progressive, we say. Progressive is like moving wave, the wave that travels. Okay, 2 progressive waves combine and they form this stationary wave. Okay, so wave that is not moving. What is the difference between stationary wave and progressive wave? Progressive wave, every single particle get to be the amplitude. Every single particle get to have the amplitude like this. Once the wave is here, this particle gains that amplitude. And as the wave travels to the right, this particle here now gains the amplitude. So every single person get the chance to gain amplitude. But for stationary waves, only that specific particle gains the amplitude here. That means it does not travel. It is kept at a fixed position. The amplitude is kept at a fixed position. So it is not traveling. What is the difference in terms of the energy? One, the energy travel. The other one, the energy is confined, is kept in one place. Okay, so you have a lot of energy that is double the amplitude, right? Double the energy that is kept in one space. Okay, that is confined in one space. And this, how does that create sound from the musical instruments? How does the guitar string create sound? First, you have the stationary wave form on the string. And then once you have the stationary wave, because the amplitude is double, so you have resonance. Okay, it has enough energy that the string moves up and down. Once it moves up, it pushes the air. Okay, it pushes the air around it, and then it moves down again. The string moves down, and then it pulls the air again. So this push and pull the region of air around the string create the compression and the rarefaction. the longitudinal wave. Okay, so you have this string moving up and down, so it creates a compression, rarefaction, compression, rarefaction, compression, and this travel as longitudinal wave reach our ear and we hear the sound. Right? So resonance, the resonance of the strings or the resonance of the sound wave in an air column inside the flute, in a saxophone, in a vuvuzela, okay? These are all based on stationary waves. It is the energy stored in one place and it is able to create this resonance. All right, so that's the basic for stationary waves. So things that you need to know is that they will ask you, okay, is the wave traveling? So you need to know there are three. You've got two progressive waves that has a certain speed. Yes, it has a certain speed. And then one stationary wave. And this stationary wave is formed by the combination of these two progressive waves. So oftentimes when the question asks you to calculate the speed is referring to the progressive wave, not the stationary wave, because the stationary is not moving. Okay, now next part, we look at what are some of the patterns that you will see when you vibrate a string. There are many patterns, not just one. This is just one of it. Okay, take a string with a certain length. Now I actually have a diagram. I'm going to use the next slide because I have this diagram already drawn on the slide. Let me go to the next slide. Okay, this one. Let's take a string with a certain length. So again, we have two notes over here, right? So when we pluck it, the first pattern that you will see, this one. Two note, and in between there's just one antinote. That's the first one. And this one, we give it a name. We call it the fundamental note. Or you can call it the first harmonic. Or the natural tone. Okay, the very basic one. Now, and then the second one is two note, and then you have this like this, just like the one that I drew just now. Okay, so you have created the next one up is you have created one note here, and then you got two antinote. Here is one antinote, here is another antinote. Okay, antinote is where the constructive interference happen. So two crests add up or two troughs add up. So they have double amplitude. Right? Now, this pattern, there's one easy way to, you don't need to memorize the pattern. You just there's one easy way to draw it like this. You just draw one wave. You draw one wave like this. Okay, now, because our string, both sides got note, right? Note on the left side and note on the right side. You start with here. This is definitely a note. Where is the next note on this wave? The next note is over here, right? The next note is over here because that would be antinote. Note is the one, remember, note is the one that has no amplitude. So the next note is over here. So that means I only take this part of the wave. That becomes my first pattern. Okay, you see here, this one is my first pattern. Then the second pattern, how do you draw it? You just take the next note. Where is the next note? After this is this one, right? This one. So this one, that means I take the wave from here all the way to the next note. That becomes my second pattern. This one, from here to here. Okay, so then you can guess the third one already. The third one, that means you go to the next note, which is this one. And how many waves are there between the first one and this one? How many waves are there? Like this, like this. So you draw this one, this, and then 1.5, right? 1.5 wave between this node and this node. So you just take two nodes, and then you see from the diagram, okay, how many waves can fit between these two nodes. So the third pattern, you got two nodes, and you have here and this one like this, right? How about the last one? The fourth pattern. The fourth pattern, again, we take the next node, this node. Okay, how many waves can fit between the first one and the last one? 2 waves, 1, 2. So this pattern, you get 2 waves. 1, 2. And then you have like this. Here, one here. Okay, if you want to label, then here you have 3 nodes. This one you have 2 nodes in between, and this one you have 1 node, and this one no node in between. So the common 4 pattern, the first 4, or we can say the first 4 harmonics. Okay, so this is first harmonic. The second pattern, we call it second harmonic. Second harmonic. And this one is third harmonic. And last one, this is the fourth harmonic. When you pluck a string, all these patterns, they form together. Okay, yes, all these patterns, they form together. Sometimes they form the fundamental, but the second harmonic is still there. The third harmonic, the fourth harmonic is also there. They form at the same time. Okay, but the one that has the greatest amplitude is always the fundamental mode. That means when you plug a string, the fundamental mode is the one with the greatest amplitude. And on the side, you get the second harmonic, you get the third harmonic, you get the fourth harmonic, but that is less significant. But it is there. Okay, it is there, less significant. The most significant is the fundamental mode. Okay, now here we're going to look at, based on this 4, how do we calculate the wavelength and the frequency? You see the first one, very easy. The length of the wire, we're going to take, okay, just length. And how many waves in this length? From here to here, how many waves? This is half a wave, right? Half a wave. So I'm going to write length equals to half of the wavelength. Move this over there. I get the wavelength equals to 2L. So we know that velocity equals to frequency lambda. I just express the frequency in terms of the rest. So we get frequency V over lambda. Put it here, frequency equals to V over 2L. Okay, because this is the fundamental mode, so I'll call this the fundamental frequency. Fundamental frequency. Okay, second one. Length equals to how many waves kept in this length? 1 wave, right? So length equals to lambda. Frequency equals to V over lambda. So that's V over length. Okay, let me box this. We have this one, first one, and we have this one, second one, right? Third one, length equals to how many waves? This one. From here to here, that's 1 wave, and this is half, so 1.5. 3 over 2 lambda. Again, we make lambda equals to 2L over 3. And then F equals to V over lambda. F equals to 3V over 2L. Box this. Do one more for the last one. Length equals 1 wave, 2 wave, 2 lambda. So lambda equals to length over 2. And we have frequency equals to V lambda. That is 2V over length. Here. That means the first harmonic, second harmonic, third, and fourth harmonic each have different frequency. Okay, so let's say you see here the second harmonic. This one I can express it as F equals to 2V over 2L. Right? So if I cancel it, it get the same thing. So 2V over 2L. And if this one, I can write it as 2 bracket V over 2L. What is this? V over 2L, this is my fundamental frequency. So I can write 2 fundamental frequency. In other words, the second harmonic is twice the fundamental frequency. Again, the third harmonic, I can also express it as F equals to 3 V over 2L. So that's 3 times of the fundamental frequency. And again, the last one, this one I can write it as F equals to 4 times V over 2L. You simplify, you get the same thing here. Okay, so this one, again, it is the fundamental frequency. So this is 4F naught. From F naught, first harmonic, second harmonic, third harmonic, and fourth harmonic. All these frequency come together to our ear and it forms a certain tone. If the fundamental frequency is 100 Hertz, your ear is also hearing 200, is also hearing 300, and is also hearing 400 Hertz together, and it gives you a sound, it gives you a tone, a particular tone. Okay, so all the patterns, they form together in the stationary waves in a string. Which one you hear the loudest? Again, it is always the fundamental mode that you hear the loudest, which is the 100 Hertz. Okay, but this one is very soft. It's very soft. It's very hard to hear all these frequencies. So we can say that you are hearing the integral multiple of the fundamental frequency. Integral multiple, so it's like 1 time, 2 time, 3 time, 4 time, 5 times of the fundamental frequencies. Okay, so this one, again, the fundamental mode, we can call it the natural. This is the natural tone. So if they say the natural tone of the string, that is the loudest that you hear. So suppose that, let's say I want to hear the second harmonic. I want to hear this louder. What do? If I want to hear the second louder, then I would create a note in the middle like this. How do I create a note in the middle? I press the string. Okay, I press the string. By pressing the string, I have created a note in the middle of the string. And by doing that, now I'm hearing this one the loudest, the second one. So I'm hearing 200 Hertz, the loudest. And 200 Hertz is slightly higher pitch than the 100 Hertz, right? So frequency higher, higher pitch. So that's why in the guitar, when you hold down the string, what happened to the pitch? You press the string, it becomes higher pitch. Okay, if you want to make it higher, what do? You press even more, like closer to the body of the guitar. Okay, now, so higher frequency, you hear thinner sound. So it all comes from the length of the string. Different length of strings, it has different fundamental frequency. So let's say if I have a string that is certain length, okay, let's do like 0.8 meter, then it gives a certain fundamental frequency. We can actually calculate that. Later, I'll show you how to calculate that. Based on the length, based on the tension, and based on the mass of the string, it gives a certain fundamental frequency, the F naught. So let's say we have this string here. If I plug this string, then what frequency do you hear? Again, you are hearing the integral multiple of the fundamental frequency. So if I plug this string, then you will hear F naught, you will hear 2 F naught, you will hear 3 F naught, you will hear 4 F naught. All of this come together. If I take another string that is shorter, that is longer, 1.2 meter, then it has a certain fundamental frequency also, F naught prime. Different, okay? It's different from this one. When I plug the string, I play the string, it gives me what frequency? It gives me F naught prime, it gives me 2 F naught prime, it gives me 3 F naught prime, 4 F naught prime. That is the meaning of harmonics. Okay, what is harmonics? It is the integral multiple of the frequency. So if you study music, if you take like piano classes, anything, you are more familiar with this one, the word harmonics. Okay, that's the meaning of harmonics. It is a set of frequency that come together to form a tone. Right. So, okay, let me get some space. If you want to take down this, you can take a screenshot, and I want to clear this, move to the next one. So if this one, if I want to find, let's say I want to find the 12th harmonics, then what do I do? 12 times F naught, right? So I can write the general formula as N and then F naught. This one. For NF harmonic, we use the formula N F naught. So if the question, how will the question ask you? Okay, this one later I will show you a few examples for the stationary waves. What is the typical questions asked? But usually the question they like to ask, like they give you a pattern like this. They give you a pattern. This is just one type of pattern, and then they ask you to calculate. Okay, what is the wavelength? Then you need to know the formula. Frequency equals to 3V over 2L. Okay, or this one, wavelength is 2L over 3. They ask you to calculate the wavelength, the speed. Okay, these are all, you see, when you do more, yeah, you see the pattern. Always they ask the same thing. Okay, now next one, we want to know the fundamental frequency. Okay, so far what we have understood, when you everything, we understood that everything, it has its own fundamental frequency. Okay, everything has its own fundamental frequency of vibration. So how do we find the fundamental frequency of a string? It depends on a few factors. Okay, what factors? Number one, okay, sorry, just now my sound is connected to the earphone. I don't know why my earphone is off but it automatically connected to the earphone. But now it's good. Huh? Yeah, now you should be able to hear me. Okay, let's continue. Right, we were at the fundamental frequency. Okay, so to find the fundamental frequency, we use from the first pattern just now, F naught equals to V over 2L. Okay, this is from the fundamental mode frequency, V over 2L. And for V, this one we can express in terms of square root the tension divided by this mu. Okay, what is this? Tension is the tension of the string. How tight is this? It is pulled. And the mu, this one is the mass per unit length. Per unit length. Okay, so 1 unit length, what is the mass of the string? This one we put in the formula, we get F naught equals to 1 over 2L square root of T over mu. Okay, please remember this. This is to calculate the fundamental frequency. And you can see based on here, it depends on the length, the tension, and the mass per unit length. So number one, length. The shorter the length, what happens to the frequency? The higher will be the frequency. So the smaller the value of L, the higher will be the F naught. So in the guitar, if you shorten the length of the string, you play higher up, then the length shorter, so you get higher pitch. Number two, it depends on the tension, how tight it is. The first string and the last string, the last one has a higher tension, okay, higher tension compared to the first one. So the thinnest string has the highest tension. It will give the greatest pitch. So again, the higher the value of the T, the higher the F naught. And number three, mass per unit length. This one you can think of it like the thickness. The thicker it is, the higher will be the mass per 1 unit length. Okay, so if the thickness, if this one is high, what happened to the frequency? The value of the frequency come down. So the thicker the string, the lower the pitch. That is why you have the thicker string, the first string of the guitar, right? The thickest, and then slowly decreases to the thinner string. Right? So here, take note again, you will need this to calculate the velocity, frequency, and length. Right? So just now we said that if you vibrate a string, it will give you a certain pattern, right? And it will give you the fundamental, the first, second, third harmonic. Sometimes the question, they will give you a something like this. They will change this. They take a string, and one end is passed through a pulley, which is hanged by a mass, and the other end is attached to a vibrator, like a frequency generator. Okay, so that this one is like you can control the vibration of the string. You can control the frequency of the vibration, like this. Now the mass here is to give tension, is to provide tension. Okay, so if the mass is, let's say, 5 kg, then you just times 9.81, or I just do 50 Newton. So 50 Newton is the tension given to the string. And here at the pulley, this side here is again a point of no motion. So I would call this node. This one is node. What about over here? The vibrator here, the string that is attached to the vibrator, sometimes it can be node, sometimes it can be antinode. It depends on the vibrator. If the vibrator is like moving like up and down like this, then it would be an antinode. Because if it's moving like this, then the particle can move up and down. So it is actually a antinode. If the vibrator is like fixed, okay, it's like fixed, but then it can vibrate the string, but the vibrator itself is not moving. So that is a node. Okay, that is a node. So again, we got two nodes. And the thing about this experiment is that I can control. I can control because I can wait. I think the audio keeps on connecting to my AirPods. Let me check my AirPod real quick. Maybe it's not in the case. Let me put it back into the case because it keeps connecting to it. So the audio is like a disconnect. Okay, give me 10 seconds. I'll be back. Sound should be okay. Huh? Okay, so let's come back. So the thing about this experiment setup is that I can control the frequency of vibration. So if I want it to vibrate at 100, if I want to create the fundamental frequency, okay, if I want to create the fundamental mode, sorry, if the fundamental mode, let's say the fundamental mode is having a frequency of 100 hertz, then I adjust the frequency generator to 100 hertz, then I will get the pattern here. And if I increase the frequency to 200, what can you expect here? You will expect to see the second harmonics. Okay, if I keep on increasing 300, then you will see the third harmonic. Of course, it depends on the string first. So first you need to find what is the fundamental frequency of this string, this one, using this formula. Okay, based on the length will just take this length over here, based on the tension, and based on the mass per unit length, you get the F naught. So if the F naught is equals to 300 hertz, then when you adjust the frequency generator to 300 hertz, you will see the first harmonic. Okay, so this experiment is the purpose of this. The purpose of this experiment is to let you find the fundamental frequency experimentally. Okay, so it's like you keep on adjusting this one until you see the fundamental mode. Then you know that is a fundamental frequency. Okay, I adjust this one. There are many patterns that can form. You will see, sometimes you will see the standing wave, sometimes you will see just a mass. Right? Other than the standing wave, sometimes it's like a mass. And then until you get the fundamental mode, then whatever is the frequency here, and then it is the fundamental frequency. Okay, we're done with the stationary waves on strings. And for the next part, we will look at stationary waves in pipe. Okay, in pipe, open pipes. But before that, I'll give you a 5-minute break. Then we will come back again. So we'll come back at 7:50. Okay. All right, let's continue on the next part, the stationary waves in pipe. Okay. Now may have experienced this when you blow across the opening, the mouth of a bottle. Okay, a sound is heard due to what? Again, resonance in the bottle. Okay, that is also based on the principle of standing waves. Or another example would be this one. You take a wine glass and you kind of like do this ring motion on it. Okay, then you hear again a sound is produced. It is also based on the principle of standing waves. Or it can be like this. The vuvuzela, okay, used in the football field, people, they are cheering for their team, right? This one, they blow inside this air column, and then again a sound is heard, which is based on the standing waves inside the tube, right? So same principle as the standing waves on the string, just a little bit different. So we are going to look at here the pattern created inside an air column. So let's say we have a tube here that is open at one end. Now, if you blow air across the tube, the mouth of the tube, here, the particle up here, it is free to move. There's a freedom of motion for the particle up here. But for the particle down here, there's no freedom of motion. So here is a note, and here is a antinote. Okay, so if you have a note here, antinote here, that is different from the previous one. The previous one is you have note at both ends. This one is note and another one is antinote. Why is this one a note? Because the air is not allowed to go to move anywhere. Okay, there's a wall here. So as soon as you blow, the air inside vibrates. The air vibrate longitudinal. Okay, because sound wave is longitudinal, right? So it's kind of vibrate back and forth like this, parallel to the wall. This one, they will ask you, the question they will ask you, how does the particle vibrate? So it is parallel to the wall of the tube, okay, because it's longitudinal wave. So as this vibrate up and down like this, and the particle at the end here, they cannot move, they cannot go anywhere. So that's why we have a note here. But up here, the particle, they can go out, they can go in. So there's antinote over here. Now, same for the vuvuzela. Okay, the one that you blow like this. This is again, you have the mouthpiece. This is where you blow it from here. This is the mouthpiece. So air insert from here, because this end is a closed end. Okay, you put it in your mouth, right? So it's a closed end. So here is again, we have a note. We have a note, a point of no motion. But out here, there is a antinote. Okay, so the air goes from here. When you blow, right, there is this air particle, or the longitudinal wave, travels to the other end, and then because here, right, you see there's an opening, but there's actually an imaginary wall here. The imaginary wall is from the difference in the density. Think about it like this. If you have a pipe, the air inside is kind of static, right? And the air outside they have more freedom of motion. They can move anywhere. But the air inside is kind of not moving that much. It's static. Okay, so we can say that there's difference in the density between here. because more particles, they are packed inside the tube compared to particle outside in the air. So inside, the air inside the tube is more denser. Here is denser, and the air outside is less dense. So it's kind of like it forms a imaginary wall between the denser medium and the less dense medium. And as the wave travel, when they go from denser to less dense, there will be reflection. Not much, but there will be reflection. Same for if the wave travel from less dense to denser. Okay, so the point is, as you blow from here, the wave goes to the opening and then it got reflected. Some wave will be reflected. Of course, most of the wave will just go out like this, but some of the wave will reflect it back. Okay, yeah? So as it reflects back, what happens? You got one progressive wave you created, and then you got a reflection of that original wave. They have the same speed, they have the same frequency, they interfere, a standing wave is created. Okay, so a standing wave is created. Now we are going to draw a few patterns of the standing wave in a closed pipe. Okay, closed pipe. One end is open and one end is closed. So the first one, how do you draw it? Same for the string. Here we have a note. I'm taking the first example here, this one. So here we have a note and we have an antinote up here. So let's draw a wave and see how many wave is between one note and one antinote. Okay, so we have the first one note. Where is the next antinote? The closest one. The closest antinote would be this one, right? This is the closest antinote. So your wave looks like only this, a quarter. A quarter, that is the first pattern. Okay, a quarter of the wave can be fit between this N and A. So how do I draw it? You draw like this. One, and then another one is like this. This is like just a quarter of it. What is this called? This we call the basic fundamental mode, or the first harmonic. So this is the vibration of air particle. Just now that one is the vibration on a string. Now the second pattern, the next one up, we go to the next antinote because we know that this must be note, this N must be antinote. So we find the next antinote, which is over here. How many waves can be fit between here? From here to here, that's like 0.75, right? 0.75. Okay, so let's draw it here. Like this, then like this. So in the middle, we got one note. This is antinote, and this is another antinote. This is the second harmonic. Third and fourth. Okay, you can even do it yourself right now. Third one, the next antinote is this one. Okay, so this one is like one wave and 0.25. So we do like one wave, 0.25. One wave, 0.25. Okay, this is the third one, third harmonic. And let's do one more, last one. The fourth one is over here. So that's one wave and then 0.75. 0.75. So we have one note here. 1, 2, 3, like this. 1, 2, 3, like this. Okay, so 3. This is the fourth harmonic. In between, we got how many note? Here is one antinote. In between, we got one note, two note, three note, three in between. Okay, if you look at the curve, you got one note, this one, right? And this one, and this one. Between this one and this one. Okay, so you have three notes. The third harmonic, you have two notes here. So next time, if you're required to draw this, then you just use this wave to help you. All right, so now we have the fourth harmonic. Now is to find the wavelength. Okay, the length of the tube here is equals to how many of the wavelength? This is a quarter, right? This is a quarter of the wavelength, so 1/4 wavelength. Wavelength equals to 4L. We do the same, frequency equals to V over 4L. This is the fundamental frequency. V over 4L. There's a difference between this one and the previous one. Okay, the previous one, what is the formula for the fundamental? V over 2L. This is V over 4L. Okay, second harmonic. Length equals to 3/4. Is what? 0.75, right? So 3/4 lambda. Lambda is 4L over 3. And F equals to 3V over 4L. With this. And this one I can write it as 3 times of the fundamental. Next one. L equals. How many this one? This one is 5/4. Okay, so one wave and 0.25. That's 5/4. So lambda equals to 4L over 5. Frequency is 5V over 4L. Box this. I can also write it as 5 times of the fundamental. And we'll just do a quick one for the last one. So it's 7/4. Okay, or it can be 7F0. So as you blow across the opening, what frequency do you get? Based on the length of the pipe, the length of the tube, you get the fundamental, you get 3 times the fundamental, you get 5 times, you get 6 times. You see the pattern. We got F0, and then we got 3F0, 5F0, and 7F0. This is like all odd numbers, right? Odd numbers. So if I want to find, let's say I want to find the NF harmonic. Let's say the 50 harmonic, 50th harmonic. Then what is my formula? I put 2N minus 1 F0. Okay, so as long as you know the fundamental frequency, then you can find whatever harmonic that you want. So as you blow, is it all coming together? Yes, all this you hear, they come together at the same time. You are hearing the odd multiple of the fundamental frequency. What is the difference between the first one, the string, and this one? There is a difference, yes. The difference in terms of like the sweetness of the sound. The odd one is like something is not as sweet as the even as the multiple one, because there are some frequency that's missing, like the 2, the 4, Okay, the evens are missing. But the first one, you got all frequency involved, right? You got the F naught, you got the 2F naught, you got the 3F naught, you got the 4F naught, all are involved. So this, it sounds like it sounds more complete, something like that. Okay, so there is a difference in terms of the sound quality between this one and the previous one. Okay. Next one. Okay, let me go to a new slide. Right, so how do we determine the wavelength experimentally? So we can find the wavelength experimentally using the concept of stationary waves. So this experiment setup looks something like this. We need to have a wave source. It can be sound wave, it can be any. Okay, let's just do microwave, electromagnetic. Okay, microwave source that is sending microwave out to a reflector. Okay, so we have a reflector here. Now the waves travel to the reflected wave, to the reflector, and then reflect back. They interfere. Standing wave is formed. Okay, if I put a detector in the middle, then what can you expect to get the signal from here? If let's say I put a detector in the middle and then I slide the detector across, the question will always ask like that. Okay, how do you determine, how do you show that a standing wave is formed between the microwave and the reflector? How do you show that? Okay, then you take a detector, you slide the detector from the left all the way to the right. What is the observation? You will observe that, you will see that the signal of the wave, the amplitude of the wave, it will be maximum at some point, it will decrease down to minimum, and then it will come back to maximum, and then decrease down to minimum and come back to maximum. That shows that a standing wave is created between the source and the reflector. Why? You see, let's take one pattern. Okay, let's say we have a standing wave, we take pattern 2, like this. It can be any pattern, right? Depending on the distance. So a standing wave created like this, we have node, and another node in the middle. We have an antinode here, antinode here. Okay, so remember, node is what? Node is when the two waves destructive interfere. 0 amplitude. Antinode is when they constructive interfere, you get double the amplitude. So as you pass this detector from left to right, let's say you start from this antinode here. That is, you are going to get the maximum signal, okay, maximum microwave. Okay, you detected the max. From here, as you slide across, what happened to the signal, the amplitude? It decreases down to 0. And then as you go from here to another antinode, the adjacent antinode, it comes back to maximum. And as you slide further, the process repeats. Maximum, minimum, maximum, minimum, maximum, minimum. That shows that a stationary wave is created, right? Okay, and then how do we use to calculate the wavelength? Let's say I want to calculate the wavelength of the microwave. Then I would place the detector, okay, from one point. I will slide it across. I find the distance between two maximum reading, which is from here. This is the first maximum. This is the next maximum. As I slide across from here, to the right side, I know the distance traveled, right? I know the distance traveled. And then I also know that from one antinode to the next antinode, this is like a half of the wavelength. Half of the wavelength. Is it one whole wavelength? No, not one whole wavelength. Because you're going from here, right? Down here to another antinode, the next one. Not this antinode, the next one antinode. That is one wavelength. So from here to here, it will be half a wavelength. Okay, so the distance here, you know, the sliding distance, and then you know that distance is equals to half the wavelength. So we can do simple calculation. So just take d equals to half lambda, and then lambda equals to 2d. So you know that the wavelength is twice the distance traveled. As long as you find the distance between the max and another max. Or you can find the distance between the minimum to another minimum. Okay, in the case of sound, if this was a sound wave, then you can hear where is the loudest sound. The loudest sound, and then you slide across the sound volume diminished, and then again it increases to loudest. So you know that it is the next antinode. Then you take that distance. Or you can find a point where there's no sound. And then you slide, the sound increases, and then come back again, no sound. Then that is the 2 points. Okay, any 2 points you can find. So for the sound wave, we would use, okay, we put like a loudspeaker, and then we put another reflector. We put a microphone. Maybe we can connect to a CRO, right? CRO will show the wave, so easier. Straight away you see from the wave, you see the amplitude decreases and then increases, decreases, increases as you slide across. Okay, so let me write it here. Wavelength is 2 times, right? 2 times the distance from maximum and the adjacent maximum. Or it could be from or minimum to adjacent minimum. This is one important thing to take note of, this one. Other than this method, is there any other method to find the wavelength? There's another one. Okay, and we're going to look at that one. This one finished, huh? I clear this, huh? Okay. Another experimental setup is you can take a column, can be a measuring cylinder, okay, that filled with water. Okay, then you clamp it. Actually, I have a video for this one. Later I'll show you one video for this experimental setup. Okay, so you have a retort stand in the middle. Excuse my drawing. Right, something like this. So basically you have a long tube that is filled with water. This one, why you have this one is just to give the pressure to the water so that it doesn't fall down like this. It doesn't drain out like this, okay? So just to keep the water at this level. All right, then you take a tuning fork which has a fixed frequency, and then you vibrate the tuning fork. Of course, this tuning fork, you need to know the frequency. You need to know the frequency of the tuning fork, and then you vibrate the tuning fork. Now, the reason they use water is this water acts as a reflector. Okay, it acts as a reflector. So basically, you create a standing waves, right? So the wave like this hit the water, and then it reflects back like this. And then you hear a loud sound when the standing wave is formed. Again, remember, standing wave is resonance, right? So you hear a loud sound when the standing wave occur. There are how many positions? You got the first harmonic, second, third, fourth harmonic, right? So the observation is this: as you slowly increase, as you slowly drop the level of the water, you will hear a series of loud sounds. That is the first harmonic, second harmonic, third harmonic, and fourth harmonic. Okay, let's say you start at the very top, and then slowly you decrease the level of the water until a certain length. Then you will hear a loud sound. That means the first pattern, the fundamental frequency of the stationary wave is formed. Okay, and then you continue to decrease the water until the next loud sound you hear. Okay, that is the another stationary wave. That could be the second harmonic. Okay, so again, this one is also can be used in calculating the wavelength. So if you know this is the first, let's say you hear the loud sound here, so that's the first harmonic, and then you know the length also, right? You can measure the length, you can measure the frequency, then you can measure the wavelength using the first fundamental mode position. Okay, what is the formula? F naught equals to V over 4 length. Okay, you can find the speed of the sound, all that. Experimentally. Okay, I want to show you one video. If you see the video, then you know in more detail how it works. Let me just find it. I think I have it in my file. Okay, after the video, then I'll show you another examples how to calculate. Then it'll be a wrap for today. Okay, this one. Share screen. Okay, you should be seeing the video window. And let's check the sound first. Adjust your volume. Later, suddenly adjust the volume on your end.
Okay, in this demonstration, we're going to be talking.
Okay, the sound okay? If there's no sound, let me know. Let me replay the video. This is one experiment on the standing waves. Huh? So you observe when the standing wave formed, you'll hear the resonance of the sound in the pipe. Okay.
Okay, in this demonstration, we're going to be talking about resonance, particularly pipe resonance. I have a resonance apparatus here with a plastic tube attached to a water reservoir. Now, I can change the depth of the water in the tube by changing the height of the reservoir on the bar. I have a tuning fork over the top of the tube here, and as I hit the tuning fork, you can see over here I have an oscilloscope and a level meter showing you the frequency. It's also picking up my voice, so ignore that part. When we get to the resonance of the tube, I'll not speak. But you can see the amplitude here is not very high. We can use the tube to resonate the frequency of the tuning fork in a way that will make the amplitude greater. We can calculate what that depth needs to be. Up here on the board, I have the values we'll need to figure that out. First of all, we need to start with the speed of sound. The speed of sound in this room is 1,050 feet per second. We need to convert that to centimeters per second because our tube here is labeled in centimeters. So in centimeters per second, that's 32,020 centimeters per second. The frequency of our tuning fork is 523.2 hertz. To figure out the wavelength of that frequency, we take the speed of sound, divided by the frequency, and we end up with 61.2 centimeters. That's the wavelength of 523.2 hertz. Now, the depth we need to dial in on the tube is going to be 1/4 of that wavelength. So we take our 61.2 centimeter wavelength, divide that by 4, and we get 15.3 centimeters. So over here, I'm going to raise the level of the water reservoir, and we're trying to get the level of the water to match this mark, which we've dialed in already at 15.3 centimeters. So here we go. I'll raise it up. And you should be seeing now the water level rising. And I'll hit the tuning fork, and we'll wait for the amplitude to get greater as we reach our 15.3 centimeters. Almost there. There it is. See how greater the amplitude is now on the oscilloscope. What's happening now is our tube is resonating the frequency of the tuning fork. I can prove it by moving the tuning fork off the pipe. Okay? So this concept of pipe resonance can be found in musical instruments such as wind instruments. The idea being you can change the depth of the pipe of a clarinet or a flute by covering the holes. And as you cover the holes, you're changing the depth or the length of that pipe, and a different frequency resonates. But this concept of resonance can also apply to boxes and rooms and strings found in other musical instruments, and just in sound that propagates naturally in space. So keep this in mind as we study more about wave propagation.
Okay, right. Okay, we'll look at a few examples of the stationary waves, then I'll give you the exercises. Okay, example 1. Stationary wave is set up on a wire of length 0.93 so that it vibrates at 120 Hertz. Fundamental frequency is 40. Draw a sketch of the stationary wave obtained. Okay, so fundamental frequency, let's write it down. F note is 40 Hertz. And what is the frequency of the stationary wave? 120, right? 120. So we want to sketch the stationary wave, meaning that first you need to know which harmonic. Is it the first, second, third, or fourth? How do you find which harmonic? You look at the frequency, right? So if the fundamental frequency is 40 and the stationary wave frequency is 120, how many times of the fundamental frequency? The frequency is 3 times of the fundamental. Okay, so if it's 3 times of the fundamental, that means it is the third harmonic. Right, so third harmonic, how do you draw a third harmonic? Okay, let's draw a wave like this, and then we start with string. This is string, right? So 2n, we have note. We have one note here. What is the closest one? This one is the closest one. That is the first harmonic. Second harmonic will be here. Third harmonic will be here. So you take this region. Okay, so that's our sketch. We do like this, and then like this. B, calculate the speed of the wave. Okay, speed of the wave. We need the frequency. We need a wavelength. So frequency already given, you need a wavelength. So you get wavelength from the pattern here. This is the length of the string. Is it given? Yes, it's given, right? So 0.93 meter. And length equals, here is 1.5 wavelength. Okay, then you can find the wavelength. Wavelength equals to 0.93 divided by 1.5, we get 0.62 meter. And then we put it here. V equals to 40 times 0.62, we get 24.8 meters slash second. Okay, example 2. Signal generator is set at 152. 10 loops fit the length of the vibrating length of a string exactly. The string is of length 2 meter and the mass on the end of it is 0.72 kg. Calculate the mass of the string. Okay, let's write down what we know. We want to find the mass of the string. So we know velocity equals to square root of tension over, this is what? This is the mass per unit length, right? So if we know the mass per unit length, then we can find the mass because we already have the length of the string. Okay, if you find the mass per 1 unit length, you just times this 2 meter, then you get the mass, right? So we want to find the mu. Okay, is the tension given? Yes, tension is given 0.72 kg. You times 9.81, you get the tension. What about the velocity here? So you have to know the velocity as well. To find the velocity, we can use Vf lambda. So you need to know the frequency, 152 Hertz, and the wavelength. Now it says here 10 loops fit the length of the vibrating length. So you have 10 loops, you have something like this, right? Okay, so 1, 2, 3, 4, you have 10 of this in the length of 2 meters. So you just calculate lah, divide this one. What is the length per loop? Length per loop. So length per loop, 2 meters divided by 10, 0.2 meters. So one loop is 0.2 meters. Wavelength is how many loops? Wavelength is 2 loops. Okay, from here to here, this one wavelength. So 0.2 times 2, 0.4 meters. And then we find the V. 152 times 0.4. 60.8 meters/second. And we put it here. Okay, so get the mu. Mu equals to 1.91 times 10 power of -3. Mass per unit length, so unit is kg m minus 1. Two meter, so mass equals to 1.91 times 2 meter. You get 3.82 times 10 minus 3. This is the mass, kg. So we can put it in 3.82 gram. Okay. Example 3, last one. Oh, example 4. A steel wire of mass 5 times 10 power of -4 kg and the length of 0.5 stretched with a force of 88.2. Okay, determine the mass per unit length of the wire. We want to find the mu. 5 times 10 minus 4 kg. We divide by the length of the wire. 0.5 times 10 minus 3 kg m minus 1. Velocity of propagation of a transverse wave in the wire. Okay, this velocity is referring to the progressive wave, not the standing waves. V equals to square root tension divided by this one equals to square root of 88.2 divided by 1 times 10 minus 3. 297 meters per second. C, find the frequency of its first, second, and third harmonic. First one looks like this. Okay, so the fundamental mode, we have two nodes here. So length equals to how many wavelength? This is half a wavelength. So wavelength is 2L, and from the formula, V over lambda, V over 2L, right? So we use this one. So F equals to speed you already got, 297 divided by 2 times 0.5, the length of the wire. And this is actually the fundamental mode. So we have the fundamental frequency equals to 297 hertz, because here you get 1, right? So over 1 is the same. So the first harmonic or the fundamental is 297 hertz. To calculate the second and the third, you just need to times 2 times 3, because you know second one is 2 F note, third is 3 F note. Okay, 2 F notes, so 2 times 297, you get 594 hertz, and this is 3 times 297, you get 891 hertz. So that's your answer: 297, 594, and 891.